Hello, everyone, and welcome to the third presentation of the Water Resources Institute, Water Connect, Water and Health Seminar Series. And during this seminar series, we're looking to highlight research on connections between water and health. My name is Kende Ojasanya, and I'm a PhD candidate here at the University of Vermont. And I'm very excited to introduce to this talk by Raju Badireddy with UVM's College of Engineering, Mathematics and Sciences, entitled Enhancing Water Safety Through Sensor-Based Smart Monitoring. Dr. Badireddy is a leading researcher specializing in sustainable membrane processes and environmental nanotechnology, with a particular focus on water and wastewater treatment, as well as resource recovery. His interdisciplinary work advances the development of sensor-based smart monitoring technologies to enhance water safety. He pioneers innovative techniques like enhanced darkfield-hyperspectral imaging microscopy for detecting engineered nanomaterials and contaminants in environmental and biological samples. His recent projects address critical challenges such as PFAS, fade and remediation, green nanomaterials development, membrane anti-fouling, and nutrient recovery. Dr. Badireddy's expertise bridges cutting-edge research and practical solutions to safeguard water quality and public health. So this talk will last for about 30 minutes and 15 minutes of Q&A at the end. And please hold on to your questions till the very end. And we welcome our remote guest. If you're joining us via Zoom, you can enter your questions into the chat box at the end, at any time during the presentation. And I will now turn the floor over to Raju. Thank you, everyone.
Thank you, Kennedy. Thank you all for coming to this talk. It's a wonderful afternoon, but you chose to stay in this basement and listen to my talk. Grateful. Also, I want to thank Beverly Van Pol and Hannah Fisher for the invitation and organizing this talk. I was seeing these talks, Water Connect, and different people presenting. I was hoping one day I'll get to present, and the day has arrived. Thanks again. So in this talk, I'm going to present some of the progress that we are making in sensor development and how we are using it to ensure water safety and safeguard the public health and so on. This particular piece of talk is a part of a bigger project. We call this AquaClimb. It stands for Advancing Water Quality and Climate-Informed Water Management through Enhanced Sensor Networks and Community Partnerships. So community partnership is a big component of this big project. But today I will mostly talk about the new novel sensors that we are developing and how we are using it to monitor different contaminants of concern. Okay.
Right. That's perfect. Is it on?
Oh, okay. Thank you. It always happens at the beginning of the talk.
No, we tested this.
I'm excited.
We might have to use the key. We'll play with it. Oh, just doesn't want to go. Okay. Sorry about that. Enter.
Enter. Okay.
That's a new one.
That's cool. All right. So, we all know, right? We are very familiar with the climate change impacts we experience every day. the rising temperatures, heavy precipitations, rising sea level, and changing climate patterns, they are severely impacting the water availability, the shortages, especially for drinking water and agricultural use. And also because of this climate change impacts, the surface waters, groundwaters, they are getting churned up. All the masses are, moving across different water bodies and changing the water quality and so on. When these processes happen, the constituents are actively transported into the water body and increasing the concentrations of various constituents. And some of those constituents are very toxic to human health, right? So in this kind of scenario, how can we, measure them and also get information about the levels of these different contaminants so that we can protect human health and so on, right? So a recent study showed that about 5.5 billion people would be exposed to polluted waters by 2100. Currently, about 2 billion people already struggle to access clean water. And there are many reasons, like, especially in the developing worlds, the poor economic growth, severe climate change impacts, and population, all these are kind of altering the water quality. With increasing population, there's a huge demand for water, right? But if you look at it, the total water on the planet is constant. The volume is constant. We cannot grow water. We cannot generate water. We have to use whatever is available to us. And when things are getting churned up and we are adding more and more mass is getting added to the water, and that's impacting the water quality. And the climate change is, with lots of consumption of products and so on, waste is generated, which eventually release toxic chemicals into the surface water bodies. And climate change is also, like I said, churning up the materials, masses, affecting the water quality in surface water bodies and groundwater and so on. Agricultural runoff, they carry certain constituents into the environmental surface water bodies, right? And there are communities that are highly impacted. Some of these communities heavily rely on river waters and streams and so on for their drinking water sources. But if these climate change impacts are altering the water quality, especially when they are resource constrained, money constrained, they don't have ways to treat their waters, and they are communities that are heavily neglected historically. So how can we help these communities, or how can we work with these communities to ensure water safety for all people, right? And we wanted to focus on these three extreme climate scenarios, like flooding, drought, and wildfires. When you have this intense rainfall, it's like too much water and too much contamination. When you have drought, there is no water available. That leads to another type of contamination. And when you have wildfires, they transport atmospherically certain contaminants and deposit it onto the water bodies. So the pollution doesn't have to be on site. It could be transported across countries, across continents, to pollute water. So the climate change has a huge impact on the communities throughout the continental US. And we are our focus communities are farmers and indigenous tribes or Native Americans in different states. These are the communities that feel the impact immediately from the climate change impacts. And they are all the time resource constrained, money constraints, and sometimes they are neglected, and they are communities at risk. So we want to study the waters in these three climate change scenarios, develop tools to monitor contaminant fate and transport, and see if we can get real-time information on the contaminants so that we can implement certain strategies to treat and mitigate the impacts of pollution. We have selected 3 test beds across 3 states, and in these test beds, we want to build distributed sensor networks, which will be monitoring the movement of contaminants in these water bodies. So we will be actively monitoring flooding and drought and wildfires and how these things are impacting the water quality. The first site, of course, our state, Vermont, We initially deployed sensors in Hungerford Brook, and this is predominantly agricultural. The yellow patches show the agricultural region in that that contributes to the nutrient transport. And the second site where we implemented the sensors or using sensors to monitor contaminants is the Potash Brook. It's just very close to our university. The yellow patches are the agricultural and the red patches are urban. So when you have different land use patterns, how these different human activities, the natural and the human activities are helping or helping to move these contaminants into the water and affecting the water quality. So we want to, we selected these sites for testing our sensors. Another reason is these two sites, like through earlier EPSCoR grants, these are instrumented already. There are conventional sensors, each one costs about $60,000 something. They are monitoring already various water quality parameters, including nutrients. These are the great sites for us to deploy our new sensors and also compare our data with these existing sensors and tools. So that's why we selected these sites in Vermont. And Vermont is a relatively humid climate, whereas South Dakota, that's the White River Basin in South Dakota, it's a semi-arid, which is partly humid, partly dry, but it has a great climate conditions there, the semi-arid conditions. And the Native American tribes, Navajo community or the Oglala Lakota community heavily rely on that particular water source. Contaminating that water source is a big deal. That is the main drinking water source for those communities. So semi-arid, humid, semi-arid, and the third state is New Mexico, San Juan River. So that's a very arid climate. So we have 3 different climate conditions, and there are all that river, like Native American communities rely on that river for drinking water, for their crops, for their livestock, and so on. So how these climatic conditions are impacting the water quality can be, would our sensors help to monitor the contaminants of interest? How fast we can sense, right? That's the question. Faster we get the information, then quicker we can respond and take action to mitigate the impacts of water quality. Vermont. Every year this happens, flooding, crops are underwater and water quality changes, and it has a huge impact on the rivers and lake water quality. This year especially, we experienced a severe drought in Vermont. That's another climate condition. And how to go back?
You could say Canadian wildfires.
All right. Okay. So yeah, the third condition is wildfires, right? But we don't experience that much wildfires. But those of you stayed during summer or early this semester, we can see the fog and haziness. That is the smoke coming from Canadian wildfires, right? We wait for thunderstorms to come and clear out the particulate matter that's suspended, gets suspended in the atmosphere. But once they're suspended, once they're cleared out, they end up in the water, affecting the water quality, right? So again, when it comes to South Dakota, their industries they have oil and gas. They have huge mining activity. They actually mine uranium and many other metals from the ground. These rivers are contaminated with lead, arsenic, uranium, and many other contaminants. So mining is a big thing here. And also, it's a semi-arid, but they also experience flooding. And this region, especially this region where Native Americans have, live there, they kind of, their livelihoods are severely impacted during flooding seasons. They also experience drought. And now US imports uranium from other countries, and now US is trying to be more reliant on self-reliant on getting uranium or mine uranium in US. And most of these mines are located in the, the Native American lands, and they want to mine it. And if they will start mining it more, their water quality gets impacted. So, how can we monitor, detect these contaminants, and can we do something about it? So, before this project, we have spoken with some of these American tribes, Native American tribes, and try to get input from them. How can we help? And not only we help them, but also we want to learn what are their concerns. And if we deploy sensors, there's like an ongoing conversation that's happening. It's a true community partnership. They are teaching us and how to, where to deploy sensors and how can we help them. And also that is also helping us to deploy at strategic places to monitor the water quality and so on. And New Mexico, again here, same issues. Nutrients are common in every state. The nutrient pollution, surface water bodies, that's very common. This is a very arid condition. They experience wildfires. They experience like very extreme weather. Wildfires in some season, heavy flooding on in another season. So, again, the Navajo community there are heavily impacted by these climate change impacts. They have flooding, they have drought, and they have wildfires. That's very, very rampant in New Mexico. So when these happens, once the precipitation happens, the contaminants, go and end up in the surface water bodies. We all know this, right? It's the importance of water safety. There are a wide variety of chemicals. There are some new contaminants. Some of them we know, some we don't know. There are emerging contaminants of concern. Then the radiological and biological, microbiological, all these will be, affecting if the waters are contaminated by these contaminants, human health, aquatic health, everything gets impacted, right? Traditional methods are like we use this very sophisticated instruments like spectroscopy, mass spectroscopy, metry, and we collect samples, bring it to the lab, analyze, we get very accurate information, but it's always delayed. 1 day or 2 days or 2 weeks later, we get the information. But in this 2 weeks period, many things happened. It's not the reality anymore. It was the information about the past, but not about the reality. What is going on now is very different from 2 weeks ago, right? But that's the drawback of these traditional methods. We get accurate information, but there is a disadvantage. So there is a real need for devices that can transmit information in real time about the constituents in the water. So we need some smart solutions for that. Our focus, like the sensors that we are focusing on is, of course, in addition to the nutrients like nitrogen and phosphorus, or ammonium nitrate and phosphates, we are also developing sensors to address these contaminants. For example, heavy metals, they are also common, especially in New Mexico and South Dakota. Their waters are contaminated with heavy metals. They are coming from mining, pipelines, industrial effluents. We know about their top neurological and carcinogenic effects. Most of you remember Flint, Michigan incident, right? It's lead release, contaminated and affected 100,000 people. And also it's very challenging to detect them in real time. So very slow analysis. PFAS, those are forever chemicals. They are thermally, chemically, biologically resistant. That means nothing can degrade them. They persist in the environment, they move, they bioaccumulate, and there are a lot of studies showing their links to cancer, reproductive toxicity, and so on. Look at that. EPA has pushed to set standards for PFAS. This year, now EPA is saying, it's probably all right. That's what EPA stands for now. EPA, probably all right. They don't want, even though we're showing the PFAS and impacts, it's okay. Though you don't have to follow the standards anymore for PFAS. That's the approach they're taking, unfortunately, even though the data science is there to show the impact of PFAS and so on. And the microplastics. Some of you may have worked with microplastics. It's extremely tedious process to quantify microplastics in the environment. So what if we have a sensor to measure microplastics in real time? So that's also a focus in our, again, microplastic by themselves may not be toxic, but they are like Trojan horse. Things go and stick, they transport into the environment, and fish and whatever eats it, then toxicity comes from indirectly most of the time. And radionuclides, uranium and so on. If they are present in there, they are, it's very, very toxic. And in the water, they're always, they present as a mixture. And if somebody is drinking that water with the mixture, the cocktail of these contaminants, you can imagine the health impacts that arise from this drinking from such waters. Conventional treatment, some of these things, PFAS just goes, it's blind to every treatment except for activated carbon. It can remove, but most of the things just pass through untransformed in the existing wastewater or drinking water treatment plants. So they are invisible actually. So now there's a growing need for smart monitoring. Now, if we have some device that can tell us about the levels of these contaminants in real time, that's a great advancement. So what is the smart monitoring framework? Like, we are now taking the advanced sensors, coupling it with data analytics and Internet of Things. So there is artificial intelligence, machine learning, tools, data processing, everything is like now we are building a device that can not only take the data, but it processes and provides information about the contaminants of interest. The benefits of this, having this kind of a monitoring framework, early warning about the constituents in the water, and once we know about what's moving, what's present, we can take action, right? If you remember COVID time, if we know these viruses are appearing in the wastewaters, if we know, then we would have taken action and kind of prevented the spread of virus in the community. But to do that analysis, it takes a week by the time everybody is infected, right? But if we have a device that can early warn us about their presence, that's a great thing. And then once we have the system, we can do some long-term monitoring, right? So that's the advantage of this smart monitoring framework, and that's what we are building. We are going towards that. These are the contaminants that we are currently focusing on, nutrients, heavy metals, and emerging contaminants. So like I said, this Aqua Climb project, the big project, these are the 5 objectives that we are working on for the next 3 more years or so. So we will be developing these affordable, advanced microsensors that will inform us about water quality. Then we will build these intelligent distributed sensor networks. They are like wireless and community science information, a wide variety of data that gets input into transmitted by the sensors. Then we will be modeling the climate change scenarios, biogeochemical processes, all these things goes into this modeling framework. And this information will be fed into this is one of the outcomes, decision support tools. Once this information goes in, then the policymakers and stakeholders, they can look at the data and make decisions to how to handle, mitigate the water quality, water pollution and its impacts. And then we are partnering with communities to enhance scientific literacy and convergence research, education, entrepreneurship in all 3 states. But today, I will be mostly talking about the sensors that we are building to achieve these goals. So we have been working on these sensors for about 3 years now. And we have successfully developed sensors for phosphate, ammonium, and nitrate. So we are focusing on these 3 things because they are common to all 3 jurisdictions. And when flooding happens and some climate changing, flooding or wildfires, these things move, right? And because we have the sensors, we already deployed and we are already collecting data on this. And in addition to the sensor data, we are also using conventional sensors to get some sparse data, which we can validate the sensor data. So this is also going in parallel. And while we are monitoring these nutrients, we are also trying to discover new receptors that can selectively bind to different heavy metals, different PFAS molecules, microplastics, and radioactive elements and so on. But it will take a while. We have made some great progress in the heavy metal area, but PFAS we are still researching. Microplastics we know, we finally figured out a mechanism to detect microplastics. Uranium, it will be fluorescence. Again, we are researching for receptors that can selectively bind and glow. When they glow, we can quantify these things. So we are working on these three things. So like I said, we are monitoring these nutrients, and we all know the impacts of nutrient runoff, right? The sources are agricultural runoff, industrial discharge, urban runoff, and all these things kind of discharge or release nitrogen and phosphorus into the environment. And so having the information about the concentrations of it will help us to protect water quality and human health and ecosystem health and so on. These are some guidance, like what is toxic and what is not, right? So naturally nitrates are present at 0.1 to 2 milligram per liter. Moderately impacted waters 2 to 10 milligram per liter. Heavily impacted means greater than 10 milligram per liter nitrate. So EPA's MCL is 10 milligram per nitrate. Anything higher is toxic. So similarly for phosphates, relatively they are much lower compared to the nitrate, but naturally they are less than 0.01 milligram. Mesotrophic waters in this range, eutrophic waters 0.1 to 0.35, and EPA MCL is at 0.1, 0.05 to 0.1 milligram per liter. So these are something, this will help, like once our sensors detect it, it will help us to know what are the current concentrations in the waters that we are measuring. Again, these are the conventional methods which we use for measuring nitrogen and phosphorus, colorimetric, chromatography, and so on. But these are the drawbacks, which I already mentioned. Very expensive, time-consuming, very advanced instrumentation, lack real-time data, lack data transmission capabilities. It has to be done in the lab. So our sensors, which one of the sensing mechanisms is electrochemical. These are cost-effective, portable. It enables real-time measurements, high sensitivity, very low detection limits, miniaturization, miniature capability, reasonable precision, fast response, no reagents required, high selectivity, and ease of operation. So I'm going to show some of these things in the next few slides. So the benefits of real-time measurements. It will help us to protect water and ecosystem health, and it will help us to make better decisions for water quality management. It will help us to develop best water management practices, and also by having more information about the concentrations and flow rates, we can develop better predictive models, which will then help us to mitigate the pollution impacts and so on. And it also tells us what are the sources of these nutrients. Where are these contaminants coming from, right? It will identify the sources. This will be, like I said, some of these measurements are very tedious, time-taking, but it will, with these sensors, we will be able to very quickly know about the levels of different constituents in the water. And it will also help us to kind of in real time know the impact of land use, the changes that are happening in the the environment, how they are impacting the nutrient dynamics. So these are all the benefits of this real-time monitoring measurements. So now I'm going to talk about the sensor node that we develop. This node, a sensor network is made of many nodes, right? So we developed a node, and then we will kind of duplicate them to build many other sensor nodes so that we can monitor a wide area of water bodies and so on. So let's look at the sensor node. So in the sensor node, one of the key sensing mechanisms is electrochemical. This is the heart of the sensing, right? And this technique we are using to monitor, measure various analytes like phosphates, ammonium, nitrate, arsenic, lead, mercury, and uranium. So what is this electrochemical sensor? There is a kind of a gold or copper surface. On this surface, we put a sensing membrane. If this rectangular boxes are what are called receptors. They have a chemical property that allows them to selectively bind to the specific analyte. So that's where that's a huge area of research. We are trying to discover new receptors to selectively bind to these contaminants. Right? And when the analytes go and bind, they produce a potential change. And this potential change is related to the concentration of the contaminant. So using this Nernst equation, we can measure, first we measure the potentials, that's a direct measurement. And using this equation, we can measure the concentrations associated with the potential change. And here's one example. Here you're seeing the concentration of ammonium ions as milligram nitrogen per liter, from 1 milligram nitrogen per liter to 8,000 milligram nitrogen per liter. And the lowest concentration to the highest concentration in 60 seconds, you can see very stable response from each sensor element. So this is kind of a calibration curve. Every potential has associated with the concentration. So we can get these potentials and then translate into the associated concentrations. So this is the core of the electrochemical sensing that we are developing in the lab. This is a node, and we deploy many boxes and integrate them. We have something called long-range wide area network that has the capability of wireless data transmission, suitable for both lab and field measurements. So we have already built this. Now we are working to build the modems or integrate the modems, Internet of Things, and connect it to remote monitoring and so on. So this is what is currently happening in our labs. This framework is the distributed sensor network that hopefully by the end of this year, we will have made a great progress on it. I'm calling this a first generation sensing node. You can see here, this is the actual sensor with temperature and sensing element and so on. And we have to put that or house it in a waterproof box because we deployed this in the lakes and river, and we don't want the water to go in and short circuit the circuit boards. That's why we build this. But now we are working with Professor Tian Shah. Now this second generation will be like, I can hold it in a palm. The whole sensing, that whole thing is shrunk into a palm size unit. But we are making progress on it. But this is what we used at the moment to collect data on some of the nutrients. So what are the, one of the key components in the electrochemical sensing is we need a potentiostat. So we at UVM, we built this long range wide area network potentiostat, like we call this LoRa stat. It has these certain features, energy efficiency, and it's optimized sensing strategy. We can collect information every 15 seconds if we want, or every 15 minutes. It is changeable, depending on the frequency of data collection we want, we can change it. But our first tests we collected data at every 15 minutes, which I'm going to show later. Extended operational lifespan, especially because of the batteries. But if there are no batteries, if we are now putting solar panel on it, it might go much longer. Portable, accurate, and also this wireless transmission up to 2 kilometers, we can these wirelessly communicate, transmit the data, real-time monitoring. And another exciting part is this. So the equivalent potential stats in the market is about $6,000 each. What we built is this LoRa stat, which costs $233, including 16 different sensors. I don't know if you ever purchase a pH meter. If you purchase it, it's about $400, $500, just pH meter, right? But our sensor, this stat, can accommodate 16 different sensors. Imagine that. So much information we can collect. Everything included is about, let's say, $250. So that's another affordability of these sensor boxes. And power consumption, like when they are active, about 636 milliwatts. When they are in sleep mode, very low power. And you can see the cost of electricity at the moment is 23 cents per kilowatt hour. Very small amount of energy, low cost aspect of these sensors. So how do we know our sensors are working? Are they good or any better than the commercial ones? So we compared their performance. So one of the ways to do that comparison is running a cyclic voltammetry. This cyclic voltammetry describes or gives a signature fingerprint of how a sensor is behaving. right? It will produce a single fingerprint for a particular electrochemical system. So we used some standard potassium ferrocyanide, and we collected information about the redox potentials about this compound using cyclometry. This is the trend. We varied different concentrations at a particular scan rate. It produced this signature. And look at our potential stat. It also produced signatures. We transformed and compared their slopes. You can see orange lines are the commercial and the green are our potential. So they are, our potential stat is equally good as the commercial sensor. It's very low cost, but also it's performing very well. Next what we did is we kept the concentration constant and varied the scan rate. Again, the signatures are almost identical. You can see in the linear plots, peak current versus scan rate. So this gave us confidence that our sensors are potential stats are reliable, and we can use it confidently for measuring the concentrations. So that's the one potential stat. That LoRa stat is one component of the electrochemical sensing. And the other second important component is the sensing membrane. Right? So the sensing membrane, so this is the membrane that interacts with these different analytes. So that's where the engineering and the chemistry comes into picture, designing the cocktails and the membranes associated with it. So the sensing membrane has some kind of a immobilizing substrate, a polymeric matrix, a plasticizer, ion exchanger, and neutral ligand. This is the receptor that I was talking about. That's the one that we change depending on the constituent that we want to measure. So we make a membrane out of it, put it on the electrode. And the ionophores, the receptors that I was talking about, there are some commercially available. This is ammonium, this is for nitrate, and these are the two novel ones, newly synthesized for measuring the phosphate species. So we tested all three nutrients using this particular method. So after we create this sensing element, we check for all these things: working range, sensitivity, selectivity, limit of detection, reproducibility, response time, and stability, and interference of other ions. It's not just our contaminant, but there are so many other things in the water. They all will be interacting and competing. So what's the impact of their presence? So we also assess that. Then we did, first test will be in the laboratory. So here you can this is showing the dynamic response of an ammonium sensor. We varied concentrations from -10⁻⁷ molar to 10⁻², which is 10⁻² is about 7.78 milligrams nitrogen per liter. And look at the response time, it's less than 30 seconds. As soon as you dip it, we get a response. We know the potential change. Through the calibration, we can measure the concentration of the constituent. So this is the potential versus log concentration, sensitivity, and the limit of detection is 18 parts per billion, 18 micrograms per liter with our sensor. That's a very, very low detection limits. Then we check the interference of other ions. So we have a receptor. In addition to ammonium ion, there are other cations in there. They all will be, doesn't matter to them, they all will be coming to compete and coming to bind and so on. So we checked with some of the dominant species like potassium, sodium, calcium, and red is the ammonium ion response. So it has a very distinct selectivity, but there is some consistent selectivity to other cations. But we can quantify this and we can correct for it once we know. So that's the approach we are taking. So, but this has a very high selectivity, and this is a very good receptor for ammonium ion. And the next thing we check is how stable are they, right? In the lab, under highly turbulent in the mixing conditions, this is the response on day 0. And after one week, the signal started to drift. It still stayed linear, but its signal started to drift. So that means there is something going on with the membrane because it is in water, it's constantly in contact with water. Maybe something is leaching or something is sticking to it. But whatever that drift is, that is a constant drift. So we can quantify it and we can correct for it. That will again shift back to its original detection. So we are systematically quantifying all these interferences and drifts and so on. Then we can create a compensation factor, which will correct for the actual concentrations. This is for the nitrate. You can see here a very dynamic response within 13 seconds. We change the concentrations 10 to the minus 7 to 10 to the minus 2. The limit of detection is 62 parts per billion, 62 micrograms per liter. Again, this is the linear range in which it is, they are very good. At 10 to the minus 7, the potentials are, it's not very sensitive, it's not linear, the calibration curve. So we chose 10 to the minus 5. So 62 parts per billion is the detection limit for the sensor. Again, for the nitrate, we check the interference of all the other anions in the water. Only nitrite. This is nitrate, and the nitrite also seems to have some selectivity to it. But we know what's that interference from nitrite ion, so we can correct for it. But this is also very good receptor, at least the best available in the market right at the moment. Again, this sensor also showed some drift in the signal after 1 week, and it's also a consistent drift, which we can correct it. Then the phosphate. So this is these don't exist in the market. We collaborate with the chemist to synthesize these molecular receptors, and we tested them. And we tested against the mono and dihydrogen phosphate ions. This is for the mono, and that's for the dihydrogen phosphate ions. Both have a detection limit of 3.2 parts per billion. 3.2, there's not this almost identical detection limits for the phosphate. So we have these receptors, and the sensors built based on these receptors. The sensors maintain a good time stability over 1 week. There is a slight drift in the sensor response, particularly at higher concentrations. However, the linear fit remains strong. We know how much drift is there. We know what's the interference. We can quantify, and we are now developing some equations to correct and compensate for these interactions. So that was in the lab. Now let's see how they perform in the field. So we built a sensor. You can see this is the multi-array sensor. Each one is for example, this is for phosphate, this is for arsenic, this is for lead. We can put different sensing elements there, or we can triplicates of each sensor. We can deposit. We are playing with the multiple designs. Now we have 32 array sensors, 16 array sensors. We can expand very easily. We can print that in Dr. Shah's lab. So we created this new design, build this sensing sensor node, and then we deployed in the Potash Brook. This is Saul Blocher. It's Monere, the postdoc who is working on this project. She's in my lab, and Parmida, she's in Professor Shah's lab. We collaborated to build these sensor nodes, and with the help of Saul, we deployed in Potash Brook and also in the Hungerford Brook. So the first thing we did is we monitored the concentrations of nutrients for 2 weeks. And Megan, she's a postdoc of Carol Adair. She helped us with the grab samples. And these are the concentrations of nitrogen and phosphorus in Hungerford and Potash Brook. In the Potash Brook, the nitrogen concentrations are between 2.2 to 3.9 milligram nitrogen per liter. In a Hungerford, they're a little lower, 0.2 to 0.7. So that's for the nitrogen concentrations. And that's for the phosphate, for P concentrations in Potash Brook and Hungerford. They are much, much lower. This was during May, first 2 weeks of May. So for 2 week period, we collected data on these nitrogen and phosphorus concentrations. And these are the temperature profiles. Temperatures in Potash Brook vary from 10 to 16 degrees during May, and Hungerford 10 to 17 degrees Celsius. They're almost similar, but you can see their fluctuations. We'll talk about these fluctuations a little later. This is the data from our sensors. So this is the potentials and 2 weeks of time. So this potential corresponds to 0.778 milligram nitrogen per liter. The lower bound 7.78 10 to the minus 4 milligram per liter nitrogen. The data here, at the end of 1 week, we found that batteries got discharged, and then the postdoc went there and in a timely manner they replaced the batteries, and then again the data came back to normal. But this is the concentration range for the nitrate in potash brook. In Hungerford brook, there's much greater fluctuations there in the nitrogen concentrations, and you can see these are the thresholds of low and high concentrations in the Hungerford brook. Then for ammonium, again same thing. There is these are the nitrogen concentration low and high. The concentrations are in this range, and this is the Hungerford brook ammonium ion concentrations. There is much more dynamics happening in the Hungerford during first 2 weeks of May. And look at this. The receptors that we designed for phosphate, we found that receptor is also sensitive to nitrate. It's like buy one, get one free. That says, okay, but if it's not highly selective for phosphate, then you'll be in trouble, right? But anyway, we deployed it in the field and then looked at the concentrations. So these potentials corresponds to nitrogen. There's low and high nitrogen, and they stayed there. But if you look at the phosphate, it is supposed to detect phosphate. But the phosphate potentials are here, below 0 to minus 80. If these signals are here, that would be phosphate, but everything at a higher concentrations. And that means it's saying that there's more nitrate in the water compared to the phosphate, and it's not, nitrate is like dominating compared to monohydrogen phosphate or phosphate species. Same thing with the Hungerford too. Look at it, everything is saying that there is a very high nitrate, but the phosphates are low. If there are phosphates, you should have signals below 0 to minus 80. That's the range where we detect phosphates. That's why I'm saying, buy one, get one free. We are detecting more nitrate than phosphates with these receptors. Yeah, again, this is the previous one is mono. This is the dihydrogen phosphate. Again, it is showing more signal towards nitrate than the phosphate signal. Yeah, and the same characteristics with the more nitrogen, not much phosphates in the Hungerford brook. Again, like I said, we are still researching these receptors, but kind of it makes sense to me. If you look at the grab sample data from those locations, look at the nitrogen or concentrations, like 2.2 to 3.9 is the nitrogen data. Phosphates, they are very low, 0.003 to 0.017 in the potash brook and 0.003 to 0.012 in Hungerford. They are much lower compared to these concentrations. You can see why our receptor is kind of sensing nitrate and not phosphate. But if we have to see if when we tested in the lab, they are very selective to phosphate at those low concentrations. So in summary, like what did we learn from these data? We found temperature can influence the interaction between the receptor and the ion. So we need to correct for those temperature. And these fluctuations impact the way they interact, right? So some temperature compensation needs to be done. And the concentrations, we know I think this is nitrogen concentrations. So we can correct temperature. We know the actual conventional method-based measurements. We have a gram sample data. And there is also drift in the sense as if it's 1 week, we measure for 2 weeks. So there will be a significant drift. So what that drift is, and if we can transform it into an equation, then we can correct for it. Then once we correct it, then these might shift up or down. But most of the time, if we don't correct for these drifts, it will be underestimation of the concentrations. So, we are developing those equations and coding it so that we can automatically correct during these measurements. So that's happening. So in conclusion, we have very good electrochemical sensors for phosphates, ammonium, and nitrate for both lab and field. Very low detection limits, 18 microgram per liter for ammonium, nitrate, and phosphate. So low detection limits without temperature compensation. They showed a high selectivity and sensitivity, but also we saw the drift. But we know what that drift is. We can quantify that drift. But with temperature compensation, we need to implement or apply the temperature compensation based on the Nernstian equation and also material specific. Is it just the temperature or some maybe ligands are leaching or some chemical is leaching that's affecting the membrane? So once we quantify those things, we can correct it, and then we'll be able to get much more reliable data. So like I said, this is a big project that's ongoing. So we are working on building this distributed sensor network this semester and beyond. Then we are integrating this with the treatment. In South Dakota, we built a simulated basins where we can test in the lab, but it's kind of representative of a mesocosm that has inflows and outflows. We are integrating and doing that. And using the machine learning tools, trying to screen a wide variety of receptors so that out of 1,000, maybe we'll find some 10 receptors which we can test in the lab. But we are modeling these chemical species, receptors to identify the receptors, select two to different contaminants. And we are working with the communities, farmers here, and the Native Americans in South Dakota and New Mexico, and other stakeholders. We are working as a team. We are co-developing this knowledge and the technology so that we can deploy and learn from them and help them to monitor their water qualities. And one of the products will be a smart decision support tool, where it will be on a cell phone or somewhere where they can get this. All this information will be fed, and it will produce certain outcomes using which we can take certain decisions. Safe, reliable, and water supply networks. So the first funding that we got is from the GUND, which laid the foundation for sensor development. And then the Cairo led us to doing some field measurements. And NSF funding is helping us to build this distributed sensor networks and explore other sensors. Monterey and Permida, they are the ones that made these sensor nodes and distributed sensor networks happening. I'm collaborating with Professor Shah, Andrew Stroth, Carol Adair, and Megan Duffy. They're all part of this project. Yeah, with that, thank you so much for your attention, and I will be happy to take any questions.
This might be just a clarification thing. Is the whole system with the case supposed to be within the water or just next to the water?
Next to the water.
Next to the water. So then follow up on that is, I guess, do you have any concerns or setbacks trying to design these things to work in 3 different climates? Because you have New Mexico, and if you're running them off solar, right? I'm not sure what the power draw is.
Right.
I'm just curious, like, do you anticipate any setbacks, or have you run into concerns already of how to make this adaptable for all 3 regions?
Solar panels would be great for New Mexico, and for us it will be like a part of the season. The other will be, if they have on-site power, we can hook it up to that. Otherwise, we have good batteries, but batteries are expensive.
Right.
So one of the challenges that we had recently was, because the box is there, sensor is in the water, we had like an 8-foot-long cable connecting these. Cable had no impact on the signal transmission, but it's very cumbersome. Right? That's why we are now trying to miniaturize it so that, if the communities can take it and measure it on site if needed, or then there are various strategies that we can take depending on the region.
Okay.
But that's part of the work.
Thank you. Very interesting.
A couple of questions about the calibration of the sensor.
Yeah.
You showed a graph when you were increasing the concentration over time. have you done a similar test where you decrease the concentration over time?
That's not a good scenario because if I go from high to low, these constituents will go and bind, and it might alter the membrane conditions. So we wanted to, that's why we went from low, and stepwise we increase the concentration. But we can easily wash them off. That's the whole. If they go and bind and stay there, then it's useless. Right? So
I guess I'm wondering then, if you put it in a stream and there's some pollution event that increases the concentration, the next day the concentration will go down. How does your sensor
because it's a
respond?
continuous flow, whereas in the lab they are in the beaker, it's not. Everything is stuck in there. Whereas in the field, it's continuously washing.
Okay.
So that won't be a problem. It's like an instantaneous spike. You measure it, but next flow should wash off.
Okay,
So
but you haven't tested that
No, not
continuous
yet.
flow in the lab.
But the field measure, not in the lab. Yeah.
I see. And then also wondering about variation from sensor to sensor.
Mhm.
You make 10 sensors or 50 sensors and you give the same conditions.
Mhm.
How much does the
In the
noise
lab,
output vary?
right. Let me see if I can. In the lab, they are highly reproducible. In the field, you can see there is a separation between three. Those are triplicate sensors. Let me go back here. See here?
Oh, I see those.
Triplicates, those are triplicates. Yeah, you can see the variation in the field condition, but in the lab, they are highly reproducible because everything is perfect.
So do you understand why these three are different?
That's what we are trying to understand. So we have to correct for the background interference, the material specific, temperature, all these put together, then we will see why the variation. And another thing I didn't mention is all these sensors are prepared manually. So the person who prepared Monire, now she's more of an artist in depositing consistently, because if that is not perfect, then many things will change. But
have you had like any issues with any like aquatic plant life growing on the sensor and interfering with the result?
That's the fouling, right? We, in the field sensors, we saw some deposition of some gray brown matter, but you can see there's not much effect on the sensor signal. But again, that we need to see. You might have the foulants deposited, but that's not like a hard fouling. Water can still penetrate, right? But again, say for example, in the agricultural, in the Hungerford, if you have high nutrient, then you have a high microbial activity. And if biofilms form on it, then it will be very different. So my collaborators in South Dakota, they are developing anti-fouling coatings. They're looking at various nanomaterials that can inhibit fouling, but not interfere with the binding process, sensing process. So fouling is a very important issue that we need to consider. If it's like, this is only 2 weeks, but we want long-term, then fouling will happen, especially biological fouling. So that's going to be part of, built into the system.
Any other questions? Okay.
Thank you.
Yeah.
Thank you.
Thank you.
Thank you.
Yeah, so on behalf of the Water Resources Institute, I would like to thank Raju and everyone who joined us today. And please join us again on October 20th at our next seminar titled Living with Risk: How Water and Environmental Stressors Shape Health in Humanitarian and Low-Income Context, by Kelsey Gleason with UVM's College of Nursing and Health Sciences. Thank you, everyone, and have a good evening.
Yeah.